start the discussion, first let's define reaction mechanisms. The reaction mechanism describes the sequence of elementary steps that occur to go from reactants and products. In comparison, there are a certain number of ingredients needed in making a sandwich. For example, you need a patty, 2 slices of bread, lettuce, and a slice of tomato, which in this case are all reactants while the product is the delicious piece of sandwich. To start the further topics in this video, you must remember these topics in summary. First is a discussion on reaction mechanisms without equilibrium steps. Reaction mechanisms involving equilibrium steps and relating reaction mechanisms with the rate law.
For the general overall reaction, A plus B reacts to form C plus D. The experimentally determined rate law expression has the form rate is equal to K times A raised to X times B raised to Y. The values of X and Y are related to the coefficients of the reactants in the slowest or rate determining step, influenced in some cases by earlier reaction steps. Using a combination of experimental data and chemical intuition, we can postulate a mechanism by which a reaction could occur. We can never prove that a proposed mechanism is correct. All we can do is postulate a mechanism that is consistent with experimental data. We might later detect reaction intermediate species that are not explained by the proposed mechanism. We must then modify the mechanism or discard it and propose a new one. As an example, the reaction of nitrogen dioxide and carbon monoxide has been found to be second order with respect to nitrogen dioxide and zero order with respect to carbon monoxide below 225 degrees Celsius. The balanced equation for the overall reaction shows the stoichiometry, but does not necessarily mean that the reaction simply occurs by one molecule of nitrogen dioxide colliding with one molecule of carbon monoxide. If the reaction really took place in that one step, then the rate would be first order in nitrogen dioxide and first order in carbon monoxide, or the rate would be K times nitrogen dioxide and carbon monoxide. The fact that the experimentally determined orders do not match the coefficients in the overall balanced equation tells us that the reaction does not take place in one step. The following proposed two-step mechanism is consistent with the observed rate law expression. The rate-determining step of this mechanism involves a bimolecular collision between two NO2 molecules. This is consistent with the rate expression involving the nitrogen dioxide squared. Because the carbon monoxide is involved only after the slow step has occurred, the reaction rate would not depend on carbon monoxide, or the reaction would be in zero order in carbon monoxide, if this were the actual mechanism. In this proposed mechanism, N2O4 is formed in one step and is completely consumed in a later step. Such a species is called a reaction intermediate. The gas phase reaction of nitrogen monoxide and bromine gas is known to be in second order in NO and first order in bromine gas. A one-step collision involving two nitrogen monoxide molecules and one bromine gas molecule would be consistent with the experimentally determined rate law expression. However, the likelihood of all three molecules colliding simultaneously is far less than the likelihood of two colliding. Routes involving only bimolecular collisions or unimolecular decompositions are thought to be far more favorable in reaction mechanisms. The first step involves the collision of one NO molecule, which is the reactant, and one Br2 molecule, which is also the reactant, to produce the intermediate species NOBr2. The NOBr2 can react rapidly, however, to reform NO and Br2. We can say that this is an equilibrium step. Eventually, another NO molecule can collide with a short-lived NOBr2 molecule and react to produce two NOBr molecules, which is the product. To analyze the rate law that would be consistent with this proposed mechanism, we again start with the slow or rate-determining step. To analyze the rate law that would be consistent with this proposed mechanism, we again start with the slow or rate-determining step number 2. Denoting the rate constant for this step as K2, we could express the rate of the step as rate is equal to K2 times the concentration of NOBr2 and NO. However, NOBr2 is a reaction intermediate, so its concentration at the beginning of the second step may not be easy to measure directly. Because NOBr2 is formed in a fast equilibrium step, we can relate its concentration to the concentrations of the original reactants.
When a reaction or reaction step is at equilibrium, its forward and reverse rates are equal. Because this is an elementary step, we can write the rate expression for both directions from the equation for the elementary step, and then rearrange for NOBr2. When we substitute for the equation of NOBr2 in the rate expression for the rate determining step, rate is equal to K2 times NOBr2 times NO. We arrive at the equation rate is equal to K times NO2 in second order times bromine in the first order.